Hi everyone, we'll see the next lecture on extended Euclidean algorithm in the course cryptography and network security. So in the previous lecture, we have seen about Euclidean algorithm, which is helpful us to find the GCD of two numbers. Now, extended Euclidean algorithm will help us to find GCD of two numbers along with two constants S and T. So this simply we are extending this Euclidean algorithm in the extended Euclidean algorithm. So first we find GCD. Along with the GCD, we are going to find two constants S and T in which we consider T as multiplicative inverse. Now we will see about extended Euclidean theorem. So it is almost like Euclidean theorem. So where in Euclidean theorem, we have found only GCD of A comma B. Here, along with GCD of A comma B, we need to find two more variables called as S and T. So this is S and this is T. So the extended Euclidean can calculate the GCD of A comma B and at the same time calculate the value of S and T. Here the process of extended Euclidean algorithm is explained. So we know about finding the GCD. So this entire process, what we have seen in the Euclidean algorithm, that's what is there here, right? So we take R1 equal to A, we take R2 equal to B, and we check whether R2 is greater than or equal to 0. So if R is greater than 0, we'll do with the process. If R2 equal to 0, we'll stop the process. We know. In the same way, we'll take S1 as 1 and S2 as 0. We'll take T1 as 0 and T2 as 1, and we'll start the process in the same way as we are doing, right? When we do this iteration, when R2 is greater than 0, when we do this iteration in the same way, we'll make the next iteration S2 as S1 and we'll make S2 as S. Now, how we are going to calculate S? Now, how we are calculating R? In the same way, we are going to calculate S also. So if you observe here, this is the algorithm that extended algorithm which call. So here we are calculating R equal to R1 minus Q into R2. In the same way, we are calculating S equal to S1 minus Q into S2, T equal to T1 minus Q into T2. So we'll continue this process until R1 becomes until R2 becomes 0, until R2 becomes 0. So I told you no. So same as like our Euclidean algorithm, where we continue this process until R2 becomes 0. In the same way, when R2 becomes 0, GCD will be R1, S will be S1, T will be T1. T will be T1. So this is what extended Euclidean algorithm says. So we doesn't give that much importance to S. But when we go further, we'll give more value or more importance to T. We call T as multiplicative inverse or multiplicative inverse or multiple inverse. That T has more importance when we go further. At that time, we'll see. But remember, the extended Euclidean algorithm is used to find the multiplication inverse of a given variable or a given value. We see within the respect of some modulo arithmetic operations. Modulo arithmetic operations, there we see additive inverse, multiplicative inverse. That the extended Euclidean algorithm is used to find the multiplicative inverse of a given number within the modulo set. So before going to modulo arithmetic, we need to cover this extended Euclidean algorithm. We'll see how we are going to follow it. Okay, so remember the process, right? So we know how the Euclidean algorithm will work out. So we know how the Euclidean algorithm work out. So this is the part regarding to Euclidean algorithm. So along with the Euclidean algorithm process, we'll add two more processes which will find the value of S, and the other process will find the value of T. So whatever the way we are doing in Euclidean algorithm, the same will be done for the part of S as well as part of T. So, but the initialization is different. So in for finding the GCD of A comma B, we take R1, R2 as A and B. Here for finding the value of S, we take S1 as 1, S2 as 0. For finding the value of T, we'll take T1 as 0, T2 as 1. Apart from that, the entire thing is right. The entire thing is same. Like, so how do you are going to find R? We're going to find R equal to, right? We're going to find R, and in the same way, we are going to find S. In the same way, we are going to find T. In the same way, we are going to find C. So before going that, we'll see an example. We'll see the algorithm. So this is the algorithm where we are finding. So initially, we are given A comma B. Initially, we are given A comma B. From this, we need to find the value of GCD of A comma B, and we also find value of S comma T such that S into A plus T into B is equal to GCD of A comma B. GCD of A comma B. So for finding that one, as I told you, first we'll take R1 as A, R2 as B, we'll take S1 as 1, and we'll take S2 as 0. We'll take T1 as 0 and T2 as 1. Now I told we'll repeat the process until R2 becomes 0, or when we can say R2 becomes 0 is the negative condition is when R2 is greater than 0, we'll do this process. We'll do this process. So initially we know how we are going to get the quotient, that is Q, when we divide R1 by R2. When we divide R1 by R2, and then R equal to R1, R equal to R1 minus Q into R2. R1 is equal to R1 minus Q into R2, and then we take R1 as R2, R2 as R. In the same way, we will update the value of S by taking S equal to S1 minus Q into S2. Q into S2, the same equation that we have taken for R, right? R, instead of R, we'll keep it as S. So replace R with S, R1 with S1, R2 with S2. The same with for T also. The same with for T also. We replace here T equal to T1 minus Q into T2. Whenever this entire process comes, that is whenever R2 becomes 0, whatever the value that is present in R1 will be the GCD of A comma B. Whatever the value that is present in S1 will become the value of S. Whatever the value present in T1, that will become the value of T. That will become the value of T. So this is extended Euclidean theorem. Now we'll see the extended Euclidean theorem with an example, right? So you need to find GCD of 161, 28 along with the values of S and T, along with the values of S and T. Now, so to find that one, we take initially R1 as 161, and we take R2 as 28. And we initiate S1 as 1 and S2 as 0, and then we take T1 as 0, and we take T2 as 1. So this is the initial values we start with. Now, what is the thing we need to check? We need to check whether R2 is greater than 0 or not. Yes, R2 is greater than 0. So we'll find Q value. So when 161 divided by 8, the quotient is 5 and the remainder is 21. Now, right? 21. Now, how we are going to get the S value? S is equal to S1 minus Q into S2. So if you take this one, S equal to S1. What is our S1? 1 minus Q value is 5 into 0. So 5 into is 0 is 0. So the S value is 1. So that's why we got how we got S equal to 1. The same way we'll get the T value. T equal to T1, 0 minus Q. The remainder we got is 5 into T2, 1. So the value is minus 5. So this is how we got minus 5, right? This is how we got minus 5 for T, right? And this is how we got 1 for yes. Now, what happens? The procedure says, after finding Q values and calculating R, S, and T, just assign the values. Now, in the next iteration, what happens? R2 becomes R1, R becomes R2, right? In the same way, S2 becomes S1. In the same way, S becomes S2, right? In the same way, T2 becomes T1. In the same way, T becomes T2. Now to repeat this one, we need to check whether R2 is greater than 0 or not. Yes, R2 is greater than 0. Again, the same process. We first calculate the values of Q and R. First, we'll calculate the Q and R. So directly take Q. So when 28 divided by 21, q value is 1. So if you substitute here 1 minus, sorry, r1 is what? R1 is 28, right? 28 minus our q value is 1 into 21. So it will be remainder. 28 minus 21 is 27. In the same way, here, how we are getting the value of S1? S1 value is 0 minus, right? Minus q is 1 into S2 value is 1. So it is minus 1. In the same way, we'll get the t value as 6. Now, for the next iteration, what we need to do is we need to check whether r is greater than or 0. So now we'll get all the values. So before going for that one, what we need to do here, r2 becomes r1, r becomes r2. Similarly, s2 becomes s1, s becomes s2, right? T2 becomes T1, T becomes 6. Before going, now, if you want to repeat, find that value, we need to check whether R2 is greater than or not 0. So yes, R2 is greater than 0. So now again, we need to find the Q value. So 21 divided by 7 is 3. As it exactly divides, remainder will be 0. I'm not applying the formula here, just we are getting remainder only. Now we'll apply the formula for S, we'll get it as 4. If I apply the formula for t, I'll get it as minus 23. I'll get it as minus 23. Now, for the next iteration, first I need to find the values of R1, R2, right? So R2 becomes R1, R becomes R2. Similarly, S2 becomes S1, that is S becomes S2, T2 becomes T1, and T becomes T2. Now, if you want to repeat the process, let us find the value of R2. So here, the value of R2 is equal to 0, which says according to the extended Euclidean theorem, you need to stop the process. You need to stop the process. And whatever the value that we have, at the position of R1, that will be the GCD. That will be the GCD. Whatever the value that we have at S1, that will be the S value. Whatever the value at T1, that will be the T value. Now, if I apply the formula, whatever the formula we have done, S into A plus T into B will always gives you the GCD of A comma GCD of A comma B. So this is 1 minus 161 minus 161. Then what about 6 and 28? 6 8s are 48, right? 6 8s are 48 and 6 2s are 12 plus 4 16. So it is 168. Now what you are getting? 168 minus 161, you're getting 7, which is the GCD of 7. So this is the extended Euclidean theorem. Extended Euclidean theorem will find out GCD of two numbers along with values of two variables S and T. S and T. The equation for S and T is that such, like this. S into A plus T into B is equal to GCD of A comma B, and this is the proof.